To look at the stars is to look into the past, where each point of light tells its own story of how the universe was formed and evolved. Unknown astronomer. The topic of black holes and matter captivates not only our scientific curiosity but also stirs a profound sense of mystery. In the vastness of the cosmos, where light serves as our primary beacon of knowledge, black holes stand as the ultimate paradox, regions where even light itself is trapped, rendering them invisible to direct observation. They defy intuition, stretching the fabric of space and time to its breaking point, and challenging the very framework through which we understand the universe. The question they pose is not just one of gravity but one of existence itself: what happens when the known laws of nature meet their limits? At the heart of the concept lies an extraordinary tension between our pursuit of knowledge and the boundaries of that knowledge. Imagine an object so dense and massive that it not only warps space but also draws the future inwards. What was once thought impossible, a shadowy remnant of collapsed stars, has now become a window into the most extreme possibilities of our cosmos. This is the legacy of black holes, enigmatic, fundamental, and transformative in their implications for the structure of the universe. The enigma of black holes. Black holes, two simple words that evoke a sense of awe, a reminder of nature's capacity for extremes. The very notion that an object could possess such a gravitational pull that even light, the fastest entity in the universe, cannot escape its clutches, is more than just a scientific puzzle, it's a profound shift in our understanding of reality. We are accustomed to thinking of space as vast and empty, and of time as a steady, constant flow. Yet black holes challenge these assumptions. They ask us to reconsider the very nature of space, time, and matter. The journey to understanding these celestial titans began centuries ago. In the 18th century, philosophers and early scientists like Jean Michel and Pierre-Simon Laplace proposed the idea of dark stars, celestial bodies so massive that their escape velocity would exceed the speed of light. This was, in many ways, a prelude to the modern concept of black holes, yet it lacked the necessary mathematical and theoretical framework to be more than an intriguing speculation. It wasn't until the advent of Einstein's theory of general relativity in the early 20th century that the true nature of black holes began to be understood. Einstein's equations revealed something extraordinary: mass does not just sit passively in space, but actively warps the space around it. This warping of space, or more precisely of spacetime, is what we experience as gravity. The greater the mass, the more space and time are deformed. Imagine spacetime as a stretched rubber sheet. A massive object like a star creates a dip in this sheet, causing smaller objects to fall towards it. This is the force of gravity. Now, imagine that the star's mass is compressed into a smaller and smaller volume. The dip in the sheet deepens, steepens, and eventually becomes a bottomless well. This is a black hole. The point at which spacetime becomes so deformed that nothing can escape is called the event horizon. Beyond this threshold, the known laws of physics seem to collapse into a singularity, a point of infinite density where the very notions of space and time lose their meaning. In many ways, the event horizon marks a boundary not just in physical space, but in human knowledge. We cannot see beyond it, and yet we know that what happens inside a black hole is critical to understanding the fundamental workings of the universe. Beyond perception, the event horizon and the limits of understanding. The event horizon is perhaps the most evocative concept in all of astrophysics. It is a place where space folds in on itself, and time stretches to infinity. Once an object crosses this boundary, it can never return, for the gravitational pull of the black hole is too strong for anything, even light, to escape. But what happens beyond the event horizon remains one of the greatest mysteries in modern physics. To stand at the edge of a black hole, figuratively speaking, is to stand at the edge of everything we know. The event horizon is not merely a physical boundary, it represents the limits of human understanding. What lies inside, a singularity of infinite density, is a question that has driven some of the greatest scientific minds of our time to the brink of their understanding. Even now, our theories break down at this frontier. General relativity tells us that a singularity forms, but quantum mechanics, the physics of the very small, suggests that something more nuanced must be at play. The enigma of black holes is not just a puzzle for the physicist, it is a humbling reminder that the universe is far stranger than we can imagine. In this vast, dynamic cosmos, black holes are not just objects, they are the guardians of secrets we have only begun to unlock. The collapse of stars and the birth of black holes. At the heart of every black hole is a star, or rather, the remains of a star that has met a dramatic end. Stars are dynamic, living entities, powered by nuclear fusion, which transforms hydrogen into helium and releases tremendous amounts of energy. This energy produces outward pressure, which balances the inward pull of gravity. But eventually, even stars run out of fuel. For most stars, this leads to a relatively gentle death. They shed their outer layers and leave behind a dense core, which becomes a white dwarf or neutron star. However, for the most massive stars, the end is far more violent. When these stars exhaust their nuclear fuel, there is nothing to counterbalance the force of gravity, and the core collapses in on itself. This implosion happens with such force that the star's mass is crushed into an infinitely small point, a singularity. At this point, a black hole is born. The collapse of the star creates such an intense gravitational field that even light cannot escape its pull. The boundary surrounding this region, the event horizon, is the point of no return. Inside, all matter is doomed to fall inward, towards the singularity, where spacetime itself is believed to be destroyed. Black holes are not just cosmic endpoints, they are creators as well as destroyers. They shape the galaxies around them, influence the formation of stars, and may even be the key to understanding the origins of the universe itself. The broader implications: black holes as cosmic laboratories. Though black holes were once considered purely theoretical, they are now recognized as essential components of the cosmos. Their extreme properties make them natural laboratories for testing the fundamental laws of physics. As we observe the behavior of matter and energy near black holes, we begin to push the boundaries of what we know. From the peculiar phenomenon of time dilation to the emission of powerful X-rays, black holes reveal the universe in its most extreme and fascinating form. They challenge us to rethink the nature of space and time, and perhaps most importantly, they prompt us to question our assumptions about the universe itself. How does gravity work in the most extreme conditions? What role do black holes play in the evolution of galaxies? And what do they tell us about the ultimate fate of the cosmos? Black holes remind us that the universe is far from static. It is a dynamic, ever-changing place where extremes of gravity, energy, and matter collide. They show us that even in the most hostile and seemingly incomprehensible parts of the cosmos, there is beauty, order, and, most importantly, mystery waiting to be explored. Matter under extreme gravity. What becomes of matter as it ventures too close to a black hole? To answer this, we must first dispel a common misconception: black holes are not the cosmic vacuum cleaners they are often portrayed to be. Rather than mindlessly consuming everything in their vicinity, black holes operate within the same laws of gravity that govern the rest of the universe. If a star or a planet remains at a safe distance, it can orbit a black hole for billions of years, just as the planets in our solar system orbit the sun. Black holes may be incredibly massive, but their gravitational influence, outside a certain proximity, is no more destructive than any other cosmic body of similar mass. However, crossing the event horizon, the point of no return, ushers any object into a world where the usual rules of physics cease to apply. Once an object has passed this critical boundary, no known force in the universe can pull it back. From the perspective of an outside observer, time itself appears to slow down as the object approaches the event horizon, eventually seeming to freeze at the boundary. Yet for the matter itself, the experience is far more violent and immediate. As matter is drawn ever closer to the black hole, the immense gravitational forces stretch it lengthwise in a process whimsically termed spaghettification. Imagine an astronaut falling feet first toward the event horizon of a black hole. The difference in gravitational pull between their feet and head would become so extreme that their body would be stretched into a long, thin strand of matter, not unlike a piece of spaghetti. The tidal forces at play here are beyond anything experienced on Earth, where gravitational differences across distances are relatively minor. Near a black hole, the gravity on one part of an object is magnitude stronger than on another, leading to this intense stretching effect. The dance of matter in the accretion disk. Before being swallowed whole by the black hole, most matter doesn't fall directly into the abyss. Instead, it gathers in a flattened disk, known as an accretion disk, that spins around the black hole like water swirling down a drain. This swirling disk of gas, dust, and other matter is subjected to unimaginable pressures and temperatures, generating extraordinary amounts of energy. The friction and heat within the disk cause the matter to glow brightly, emitting radiation across the electromagnetic spectrum, including visible light, ultraviolet rays, and most notably, X-rays. The accretion disk is not just a passive reservoir of matter. It is a dynamic, turbulent environment where forces beyond human comprehension are at play. As matter spirals inward, accelerating to speeds close to the speed of light, collisions between particles release immense amounts of energy. This process, known as gravitational energy release, is one of the most efficient energy conversion mechanisms in the universe. In fact, the energy emitted by an active accretion disk can outshine an entire galaxy, producing the brilliant light of quasars, some of the most luminous and energetic objects in the cosmos. It's worth noting that the matter in the accretion disk doesn't fall into the black hole uniformly. The inner regions of the disk are much hotter and denser than the outer regions. As matter moves inward, it becomes compressed and heated, releasing bursts of radiation before it crosses the event horizon. These emissions allow astronomers to study the properties of black holes indirectly, offering a window into these otherwise invisible regions of space. The tidal death of stars. For many stars, a close encounter with a black hole can spell a dramatic and violent end. When a star wanders too close to a black hole, it may be torn apart by the intense tidal forces. This process, known as a tidal disruption event, rips the star into streams of gas that spiral inward, eventually becoming part of the accretion disk. The interaction between a black hole and a star is not a quiet affair. As the star is shredded, the gas that forms from its disintegration becomes heated to millions of degrees, emitting powerful bursts of X-rays and visible light. These emissions can be so intense that they briefly outshine the entire galaxy in which the black hole resides. Astronomers have observed these tidal disruption events, allowing them to witness the death of stars in real time and study the feeding habits of black holes. Interestingly, the remnants of the star don't always fall into the black hole. Some of the material is ejected outward at high speeds, creating jets of plasma that shoot away from the black hole at nearly the speed of light. These jets are often seen in supermassive black holes at the centers of galaxies, where they can stretch for thousands, or even millions, of light-years across space. These jets are a testament to the extraordinary forces at work near black holes, where matter is crushed, stretched, heated, and ultimately expelled with tremendous energy. The paradox of energy, from destruction to creation. The process of matter falling into a black hole and the energy released as it does so presents a paradox. How can such destruction generate such creation? When we imagine a black hole, we tend to think of it as an end, an annihilator of worlds. But black holes are more than just cosmic tombs, they are also engines of creation. The energy released by the matter spiraling into a black hole fuels the formation of stars, the shaping of galaxies, and the propagation of cosmic jets. In this way, black holes play a crucial role in the recycling of matter and energy throughout the universe. This process speaks to a profound and often overlooked truth about the universe: it is not static, but dynamic, constantly in flux. Even in the regions where matter is seemingly consumed and destroyed, new forms of energy and structure emerge. Black holes remind us that the universe is a place of transformation, where the boundaries between destruction and creation are often blurred. Matter, once thought lost forever to the gravitational maw of a black hole, may reappear in the form of radiant energy, influencing the cosmos in ways we are only beginning to understand. The singularity and the limits of physics. At the heart of every black hole lies the singularity, a point where the very fabric of reality unravels, a place where our familiar notions of space and time collapse into a state of infinite density. According to current theories, the singularity is a point where matter is crushed to an infinite degree, creating a gravitational force so powerful that it warps spacetime beyond recognition. The idea of infinity in physics is not just an abstract concept, it is a signal that something in our understanding has gone profoundly wrong. In the singularity, the laws of physics, as we know them, cease to apply, confronting us with one of the deepest mysteries in modern science. In many ways, the singularity represents a paradox. On the one hand, black holes are predicted by the equations of Einstein's general relativity, a theory that has been remarkably successful in describing the large-scale structure of the universe. On the other hand, when we look closely at what general relativity predicts inside a black hole, we are faced with the unsettling conclusion that time and space themselves are brought to an end at the singularity. And here, the familiar and reliable rules of cause and effect no longer function. The singular moment, when time stands still. To understand the singularity is to grapple with the profound limits of our understanding of the universe. In the normal, everyday world, we experience time as a flowing river, steadily moving forward, from the past into the future. Yet, near a black hole, time behaves in a very different way. As an object falls toward the singularity, time, from the perspective of an external observer, slows down until it appears to come to a complete stop at the event horizon. Beyond this boundary, where the singularity resides, time, as we know it, ceases to exist altogether. This raises a profoundly unsettling question: what does it mean for time to end? In the context of general relativity, time and space are interwoven into a single continuum, known as spacetime. The singularity, therefore, represents not just a breakdown in the flow of time, but a breakdown in the very structure of spacetime itself. Inside the event horizon, our everyday concepts of before and after lose all meaning. The singularity is not just a place within space, it is an event in spacetime where all paths lead to a single, inevitable conclusion, an end to time itself. The failure of physics at the singularity. The singularity is not merely a mathematical curiosity, it represents a fundamental failure in our ability to describe the universe at its most extreme. General relativity, the theory that so beautifully explains the behavior of planets, stars, and galaxies, predicts its own demise at the singularity. The equations that describe the curvature of spacetime yield results that approach infinity, signaling that the theory is no longer capable of providing meaningful answers. At the same time, quantum mechanics, the theory that governs the behavior of particles on the smallest scales, provides an equally incomplete picture. Quantum mechanics is deeply concerned with probabilities, uncertainties, and the interplay of particles and forces at subatomic levels. But when it comes to black holes and their singularities, quantum mechanics alone is not sufficient to explain the extreme gravitational conditions at play. The theory breaks down, just as general relativity does, when confronted with the infinite densities and the vanishing scales of the singularity. Thus, the singularity is more than just a theoretical boundary, it is a boundary to our knowledge. It stands as a reminder that the universe contains depths of mystery far beyond the reach of our current understanding. And yet, it is precisely at this boundary where the need for a unified theory becomes most urgent. The singularity represents the greatest challenge to modern physics, the challenge of uniting general relativity and quantum mechanics into a single coherent framework, a theory of quantum gravity. The search for quantum gravity. For decades, scientists have sought to reconcile the seemingly incompatible worlds of general relativity and quantum mechanics. General relativity governs the large-scale structure of the universe, explaining the behavior of planets, stars, and galaxies. Quantum mechanics, by contrast, operates on the smallest scales, describing the behavior of particles and the fundamental forces that govern them. Each theory works beautifully within its own domain, but when it comes to black holes, their predictions diverge in ways that are fundamentally irreconcilable. What we need is a new framework, one that incorporates the strengths of both theories while avoiding the contradictions they create when applied to extreme environments like black holes. This is the quest for quantum gravity, a theory that can describe the universe at both the cosmological and quantum scales, a theory that can explain the behavior of spacetime at the singularity. Several promising approaches have emerged over the past decades. One of the leading candidates is string theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. These strings, if they exist, could provide a way to unify the forces of nature, including gravity, into a single, coherent theory. Another approach, loop quantum gravity, seeks to quantize spacetime itself, suggesting that space is not smooth and continuous, but rather made up of tiny, discrete loops that form the very fabric of the cosmos. While these theories remain speculative, they offer tantalizing glimpses of a deeper reality, one that could explain the mysteries of the singularity and provide a path toward understanding the true nature of the universe. Yet, as with all great scientific challenges, the search for quantum gravity is as much about the journey as it is about the destination. Each step brings us closer to understanding the singularity, but each new discovery also opens up new questions, reminding us that the universe is far more complex and beautiful than we can imagine. The philosophical implications of the singularity. The singularity does not only present challenges for physicists, it also raises profound philosophical questions about the nature of reality, knowledge, and existence. If the laws of physics break down at the singularity, what does that say about our ability to ever fully comprehend the universe? Are there limits to human knowledge, boundaries beyond which we simply cannot go? In many ways, the singularity forces us to confront the limits of science itself. The scientific method is based on observation, measurement, and experimentation, but the singularity lies beyond the reach of all three. We cannot observe it directly, we cannot measure it, and we cannot experiment with it. In this sense, the singularity represents a horizon, not just in spacetime, but in human understanding. Yet, the singularity also serves as a powerful reminder of the boundless curiosity that drives science. It is precisely because the singularity defies explanation that it continues to inspire some of the greatest minds of our time. The quest to understand the singularity is not just a search for knowledge, it is a search for meaning. It is a reminder that, no matter how much we learn about the universe, there will always be more to discover, more mysteries to unravel, and more questions to ask. The singularity, then, is not just the end of space and time, it is a gateway to a deeper understanding of the universe and our place within it. Energy and information in black holes. Among the many puzzles black holes present, none is perhaps more confounding than the question of information. In the universe as we understand it, information, about particles, energy, and matter, is never truly lost. The fundamental laws of quantum mechanics insist upon this, asserting that, even as systems evolve, the information about their states is preserved in some form, even if it becomes difficult or impossible to retrieve. Yet, black holes seem to stand in direct contradiction to this principle, presenting one of the greatest paradoxes of modern science: what happens to the information carried by matter as it crosses the event horizon? To grasp the full weight of this question, consider the process of matter falling into a black hole. Whether it is a cloud of gas, a star, or even a particle, each bit of matter possesses a wealth of information: its mass, its charge, its spin, and its precise configuration in space. In our universe, information like this is indestructible, even as matter is transformed or scattered. But when this information crosses the event horizon, it appears to vanish from the observable universe, locked away behind the black hole's impenetrable veil. The laws of physics as we know them are left to grapple with a disquieting possibility: could the information be lost forever? This mystery has come to be known as the information paradox, and it has challenged physicists for decades. Central to this paradox is the fate of the black hole itself, for black holes are not eternal. According to one of the most astonishing predictions of quantum mechanics, black holes slowly evaporate over time, emitting a faint but continuous glow of particles, a phenomenon that Stephen Hawking famously described in 1974 and which became known as Hawking radiation. The birth of Hawking radiation, a new paradigm. Hawking's revelation about black holes and quantum mechanics revolutionized our understanding of these cosmic objects. His insight lay in the recognition that, at the boundary of the black hole, the event horizon, quantum effects create pairs of virtual particles. In the vacuum of space, these particles normally appear and annihilate each other in an instant. But near the event horizon, the immense gravitational field of the black hole can separate these pairs, with one particle falling into the black hole and the other escaping into space. The escaping particle becomes real and detectable, while the other is consumed by the black hole, effectively reducing its mass. This process, over eons, causes the black hole to radiate energy and gradually shrink until, eventually, it vanishes altogether. Hawking's discovery was profound. It bridged the gap between the otherwise distinct realms of general relativity, which governs large-scale cosmic phenomena like black holes, and quantum mechanics, which describes the behavior of particles on the smallest scales. It was the first theory to suggest that black holes are not entirely black, but instead leak energy in the form of radiation. Yet, for all its groundbreaking implications, Hawking radiation deepened the information paradox rather than solving it. As a black hole radiates energy and loses mass, what happens to the information that was once contained within it? If the black hole eventually evaporates entirely, does the information it consumed over its lifetime disappear with it, violating the principles of quantum mechanics? This idea, of information being lost forever, was so unsettling that it ignited intense debates among physicists, including Hawking himself. The black hole information paradox, a cosmic conundrum. To fully appreciate the stakes of this debate, consider the fundamental principle of unitarity in quantum mechanics. Unitarity dictates that the evolution of a closed quantum system is reversible, meaning that information about the system's initial state must always be recoverable from its final state, no matter how complex the system becomes over time. If information were to vanish in a black hole, this principle would be violated, throwing quantum mechanics into disarray. The black hole information paradox thus exposes a critical fault line between the two great pillars of modern physics. On the one hand, general relativity describes black holes as regions where information is irrevocably trapped once it passes beyond the event horizon. On the other hand, quantum mechanics insists that information cannot be destroyed. Reconciling these two seemingly contradictory viewpoints has become one of the most important challenges in theoretical physics. One possible resolution, suggested by Hawking's original work, was that the information might somehow be encoded in the Hawking radiation itself, gradually escaping the black hole as it evaporates. However, the nature of Hawking radiation, random and thermal in character, appeared to offer no mechanism for carrying the detailed information about the objects that had fallen into the black hole. If the radiation is featureless, how could it possibly encode the complex data about the matter consumed by the black hole over its lifetime? The holographic principle, a window into a deeper reality. In the decades since Hawking's original proposal, new ideas have emerged that offer tantalizing glimpses into the potential resolution of the information paradox. One of the most compelling concepts is the holographic principle, a bold theory that suggests the universe itself may operate like a vast hologram, with all the information contained within a volume of space being encoded on its boundary. In the context of black holes, this idea implies that the information about everything that falls into the black hole might not be lost after all. Instead, the information could be preserved at the event horizon, encoded in subtle, nearly imperceptible ways. The surface area of the event horizon, the so-called holographic screen, might hold the key to how information escapes the black hole's clutches. From this perspective, a black hole is not a bottomless pit of oblivion, but a system where the total information content is stored on the boundary and can, in principle, be recovered. This holographic view has gained traction in part through the work of physicist Leonard Susskind, who helped develop the concept as a potential solution to the information paradox. It suggests that, much like a hologram contains all the information necessary to reconstruct a three-dimensional image from a two-dimensional surface, the event horizon might encode all the information about the matter that falls into a black hole. This information would then be released, slowly but surely, through Hawking radiation as the black hole evaporates. The firewall hypothesis, a new controversy. Yet, even as the holographic principle provides one possible way forward, new controversies have emerged. One of the most provocative is the firewall hypothesis, proposed in 2012, which suggests that the event horizon of a black hole might not be the calm and uneventful boundary that general relativity predicts. Instead, a searing firewall of high-energy particles could await anything crossing into the black hole's domain, incinerating it before it ever reaches the singularity. The firewall hypothesis arises from attempts to reconcile quantum mechanics with the preservation of information. If a firewall exists, it could effectively scramble the information before anything enters the black hole, allowing it to be radiated back out via Hawking radiation without violating the principles of quantum mechanics. However, this idea comes at a cost. It directly contradicts the predictions of general relativity, which suggests that an observer falling into a black hole would pass through the event horizon without incident. This tension between the smooth spacetime predicted by relativity and the violent, information-preserving firewall suggested by quantum mechanics highlights the deep and unresolved nature of the information paradox. The universe, it seems, is not willing to give up its secrets so easily. The fate of information, a cosmic riddle. The question of information in black holes touches upon some of the most profound issues in science, not just because of the paradox it presents, but because it forces us to reconsider the nature of reality itself. Is the universe fundamentally deterministic, with information preserved at all costs, or are there circumstances, such as the formation and evaporation of black holes, where information is truly lost? If information can be lost, what does that say about the predictability of the universe and the laws that govern it? As we continue to explore these questions, one thing remains clear: black holes, once thought to be simple and unchanging objects, are among the most complex and fascinating phenomena in the cosmos. They challenge our deepest assumptions about the universe, forcing us to confront the limitations of our knowledge and to push the boundaries of science ever further. In the end, the information paradox may not just be a question about black holes, it may be a question about the nature of the universe itself. And as we delve deeper into this mystery, we may find that the answers we seek are not just about physics, but about the very fabric of reality. Black holes and the evolution of the universe. Black holes, often seen as cosmic endpoints, paradoxically play an essential role in the story of creation and evolution within the universe. Far from being mere voids into which matter and energy disappear, black holes serve as dynamic engines of cosmic transformation. At the heart of this paradox lies their dual nature. While they are points of intense gravitational collapse, they are also intimately involved in the large-scale structure and evolution of galaxies and, by extension, the universe itself. In fact, black holes are not simply passive consumers of matter, they shape the galaxies around them, influencing star formation, gas dynamics, and even the very fate of entire galactic structures. At the centers of most, if not all, galaxies, including our own Milky Way, reside supermassive black holes, titanic objects whose masses range from millions to billions of times that of our Sun. These colossal entities have profound implications for the development of their galactic environments, and their influence stretches across cosmic distances, affecting the universe on a grand scale. The galactic architects, supermassive black holes. Supermassive black holes, by their sheer gravitational dominance, play a pivotal role in regulating the behavior of galaxies. The gravitational well created by such a black hole exerts influence over the orbits of stars and gas clouds, maintaining the stability of the galactic core. The relationship between a galaxy and its central black hole is not incidental. There is mounting evidence that the size and mass of a galaxy's bulge, the dense cluster of stars near its center, are closely related to the mass of the supermassive black hole that resides within it. This correlation, known as the M-sigma relation, suggests a deep and intricate connection between the growth of black holes and the galaxies they inhabit. But black holes do more than simply sit at the center of galaxies, they actively participate in shaping their galactic environments. In many galaxies, supermassive black holes are surrounded by enormous accretion disks of gas and dust, and as matter spirals into these black holes, it heats up to extraordinary temperatures, emitting prodigious amounts of energy in the form of radiation. This energy, in the form of active galactic nuclei, AGN, can have a profound impact on the surrounding galaxy. Some black holes, particularly those in the early universe, can become quasars, blindingly bright objects that outshine entire galaxies as their black holes consume matter at incredible rates. The energy released by AGN is not just a dazzling display of cosmic fireworks, it serves a more profound purpose. The outflow of radiation and jets from a black hole can sweep through the galaxy, heating interstellar gas and sometimes preventing it from collapsing to form new stars. This process, known as feedback, plays a crucial role in regulating star formation. In this way, black holes act as cosmic regulators, controlling the pace at which stars are born and, by extension, governing the evolutionary paths of galaxies themselves. The seeds of cosmic structure, primordial black holes. Perhaps one of the most striking ideas in modern cosmology is the notion that black holes may have participated in the formation of the first cosmic structures. After the Big Bang, the universe was a hot, dense, and nearly uniform sea of particles. Over time, this uniformity gave way to tiny fluctuations in density, regions of slightly higher and lower matter concentrations. It is within these fluctuations that the first structures, galaxies, stars, and eventually planets, began to form. Among the many mysteries of the early universe is the question of how these fluctuations evolved into the complex structures we see today. Some scientists suggest that primordial black holes, formed in the chaotic aftermath of the Big Bang, may have served as gravitational seeds around which galaxies coalesced. These primordial black holes would have been much smaller than the supermassive black holes that now reside in galactic centers, but their gravitational influence could have drawn in surrounding matter, helping to form the first galaxies in the universe. If primordial black holes did indeed exist, they would have formed within the first million years after the Big Bang, during a period of rapid expansion known as cosmic inflation. During this epoch, the universe underwent a dramatic stretching of spacetime, magnifying tiny quantum fluctuations into the density variations that eventually gave rise to galaxies. It is possible that in the densest regions of the early universe, gravity became strong enough to collapse matter into primordial black holes. These black holes, in turn, may have helped amplify the density fluctuations, pulling in gas and dark matter to form the first stars and galaxies. Though the existence of primordial black holes remains speculative, their potential role in shaping the universe is profound. If they exist, they could explain not only the formation of galaxies but also some of the universe's most elusive mysteries, such as dark matter, the invisible substance that makes up about 85% of the matter in the cosmos. Some scientists have proposed that primordial black holes could account for a fraction of this dark matter, adding yet another layer of significance to these ancient relics of the early universe. Black holes as catalysts of star formation. Even beyond their role in regulating star formation through feedback, black holes may play a more direct role in catalyzing the birth of new stars. In regions surrounding supermassive black holes, the intense radiation and outflows from AGN can compress clouds of gas, triggering their collapse into dense, star-forming regions. This counterintuitive process, known as positive feedback, suggests that black holes, far from being merely destructive forces, can also act as creators, sparking the birth of new generations of stars. Consider the case of galaxy mergers, one of the most spectacular events in the life cycle of a galaxy. When two galaxies collide, their central black holes may eventually merge as well, forming an even more massive black hole. During these galactic collisions, vast quantities of gas and dust are funneled toward the center of the newly merged galaxy, fueling intense bursts of star formation known as starbursts. The central black hole, now supercharged by this influx of matter, can light up as a quasar, its energy influencing star formation across the galaxy. This cosmic dance between creation and destruction highlights the profound role black holes play in the life cycles of galaxies. They are not mere endpoints of stellar evolution, they are active participants in the ongoing processes that shape the universe, forging the stars and structures that populate the cosmos. The future of black holes and the universe. As we gaze forward into the distant future of the universe, the role of black holes becomes even more fascinating. While stars will eventually burn out and galaxies may fade, black holes could remain as some of the last remaining structures in the universe. Over incredibly long timescales, stars will exhaust their nuclear fuel, and even the largest galaxies will darken as their stars die. Yet, black holes, with their immense gravitational wells, will continue to exist, slowly but surely accreting any remaining matter around them. In the far future, black holes could dominate the late universe, with their gravitational influence shaping whatever matter and radiation still exist. Eventually, as Hawking radiation takes its toll, even the largest black holes will evaporate, leaving behind a universe that may be cold, dark, and devoid of the structures that once filled it with light. But in the meantime, black holes will continue to shape and regulate the galaxies they inhabit, ensuring that the cosmic tapestry remains vibrant and dynamic for billions of years to come. The story of black holes is not just one of destruction, but of cosmic evolution, creation, and transformation. They are both the engines and the guardians of galaxies, shaping the cosmos in ways that we are only beginning to understand. In a universe filled with mysteries, black holes remind us that even in the darkest corners of existence, there is an ongoing process of change and creation, one that speaks to the fundamental nature of the cosmos itself. Black holes as portals to other worlds. As we contemplate black holes and their mysteries, our minds are inevitably drawn to the tantalizing possibility that these cosmic titans may serve not only as engines of destruction and creation but as gateways to other realms. Could black holes, which stretch the fabric of spacetime to its breaking point, offer passageways to regions of the universe beyond our reach? Or even to entirely different universes, lying parallel to our own? These questions, once the domain of science fiction, are now the subject of serious theoretical exploration. One of the most fascinating ideas to emerge from the study of black holes is the possibility that they may be connected to wormholes, hypothetical tunnels through spacetime that could, in theory, connect distant points in the universe. Wormholes are a speculative yet mathematically grounded concept within Einstein's general theory of relativity, and they suggest a new and radical perspective on black holes. Rather than being one-way destinations where all matter is irrevocably lost, they could, in some cases, function as portals to other places and times, or even to other universes entirely. Wormholes, tunnels through space-time. At the heart of the idea of black holes as portals lies the concept of a wormhole, or what physicists more formally call an Einstein-Rosen bridge. Imagine spacetime not as a vast empty void, but as a flexible fabric that can be bent, stretched, and even twisted by the presence of mass and energy. Under the right conditions, this fabric might not only bend, it could fold in such a way that two distant points in spacetime touch, creating a shortcut between them. This shortcut, the wormhole, could in theory allow travel from one part of the universe to another, bypassing the vast distances that normally separate them. The notion of wormholes originated from solutions to Einstein's field equations, which describe how gravity affects spacetime. These solutions suggest that under certain circumstances, a black hole could be paired with a white hole, a theoretical object that expels matter and energy instead of pulling it inward. Together, a black hole and a white hole could form the two ends of a wormhole, allowing matter to fall into one and emerge from the other, potentially at a distant point in the universe or even in a different universe altogether. Though the mathematics of wormholes is consistent with general relativity, they remain purely theoretical for now. The challenge lies in the extreme conditions that would be required to create and stabilize a wormhole. Wormholes, if they exist, would be incredibly unstable, collapsing almost immediately upon formation. To keep a wormhole open, some form of exotic matter with negative energy, something that defies our current understanding of physics, would be needed. Without this exotic matter, the gravitational forces within the wormhole would cause it to pinch shut, trapping anything inside. Yet, even in their speculative nature, wormholes offer a breathtaking possibility, the potential to travel not just across vast distances in space, but across time itself. If a wormhole could be stabilized and controlled, it might allow for faster-than-light travel or even time travel, opening up pathways to the distant future or the ancient past. Black holes and the multiverse, windows to parallel universes. Beyond the possibility of wormholes, black holes also invite us to consider an even more audacious idea, that they may serve as portals not just within our universe, but to other universes entirely. The concept of a multiverse, once confined to the realm of philosophy and science fiction, has gained increasing attention in theoretical physics. The multiverse suggests that our universe is but one of many, perhaps an infinite number of parallel universes, each with its own distinct set of physical laws and constants. In this framework, black holes might be more than just cosmic anomalies. Some theories, including those emerging from string theory and quantum gravity, suggest that black holes could act as bridges between universes. As matter collapses into a black hole, it may not simply be crushed to oblivion in a singularity. Instead, the information and energy that disappear from our observable universe could be transferred to a different universe, creating a new Big Bang in another reality. This idea is especially intriguing when we consider the information paradox discussed earlier. If black holes are gateways to other universes, the information they consume may not be lost, but rather passed on to these alternate realities. In this way, black holes could play a role not just in the evolution of our universe, but in the birth and development of countless other universes, each following its own path of cosmic evolution. While this remains a deeply speculative idea, it offers a profound new perspective on the nature of reality. If black holes are indeed portals to other worlds, then the universe we inhabit may be part of a far greater, more complex cosmic structure than we have ever imagined. We might live in a multiverse where black holes serve as cosmic junctions, connecting disparate regions of reality and facilitating the creation of new universes. Traveling through black holes, possibilities and perils. If black holes are indeed portals, then the question arises, could we ever travel through them? The idea of journeying through a black hole is one that has fascinated scientists and science fiction writers alike. In theory, if a black hole were connected to a wormhole, it could offer a pathway through space-time. However, the practical challenges of such a voyage are immense. First, there is the problem of the event horizon. As we have seen, once an object crosses the event horizon, it is subjected to extreme tidal forces that would stretch and compress it in a process known as spaghettification. For any traveler, this would be a fatal encounter. Long before reaching the singularity, they would be torn apart by the black hole's immense gravitational pull. However, some physicists speculate that for certain types of black holes, especially large, slowly rotating black holes, the tidal forces near the event horizon might be weak enough to allow an object, or even a spacecraft, to pass through unharmed. Even if it were possible to survive the journey across the event horizon, the question remains, where would the traveler emerge? In the case of a wormhole, the traveler might arrive at a distant point in the universe, or perhaps even in a different universe altogether. Yet the journey through a black hole would be fraught with uncertainty. The interior of a black hole is a place where the known laws of physics break down, and no one can predict with any certainty what awaits on the other side, if, indeed, there is an other side at all. For now, the idea of traveling through a black hole remains a distant dream, one that belongs to the far future of theoretical and technological advances. But it is a dream that beckons us to imagine the possibilities. What if we could use black holes as bridges to explore the farthest reaches of the cosmos? What if they could provide shortcuts through the vast distances of space, allowing us to reach distant galaxies in an instant, or even travel to alternate realities where the very fabric of existence differs from our own? The philosophical implications, black holes and the nature of reality. The idea that black holes could serve as portals to other worlds, whether through wormholes or the multiverse, forces us to reconsider our understanding of the cosmos and our place within it. If black holes connect different regions of space-time or even different universes, then the universe itself is far more interconnected than we have ever imagined. The boundaries between here and there, between now and then, between our universe and another, become fluid and permeable, blurring the distinctions that we take for granted. This perspective also invites profound philosophical questions about the nature of reality. If black holes open gateways to other universes, what does that say about the uniqueness of our own universe? Are we one of countless realities, each with its own distinct set of laws and histories? And if so, what is the significance of our existence within this vast multiverse? Do black holes offer not just physical portals, but also portals to new ways of thinking about the nature of existence itself? The possibility that black holes may connect us to other worlds also challenges our understanding of time and causality. In a universe where wormholes and multiverses exist, the linear progression of time may give way to a more complex, interconnected web of temporal possibilities. The past, present, and future may not be as distinct as they seem, and black holes may hold the key to unlocking these deeper mysteries. The infinite frontier. In contemplating black holes as portals to other worlds, we stand at the edge of one of the most profound frontiers of human knowledge. These cosmic objects, once thought to be mere anomalies, may hold the key to understanding the very nature of space, time, and reality. Whether they are bridges through space-time, gateways to parallel universes, or engines of cosmic creation, black holes challenge us to think beyond the limits of our current understanding and to imagine new possibilities for exploration and discovery. As we continue to unravel the mysteries of black holes, we may find that the universe is far more interconnected, dynamic, and full of potential than we have ever realized. And in doing so, we may discover not only new worlds but new ways of understanding the universe and our place within it. Interaction of black holes and matter. Black holes, once thought to be inert voids that simply consume all that ventures too close, have revealed themselves to be far more dynamic and influential players in the cosmic landscape. They are not mere cosmic endpoints, rather, they are energetic engines, profoundly shaping their surroundings and, in many ways, driving the evolution of the galaxies they inhabit. As matter spirals toward the event horizon of a black hole, it enters a violent and transformative journey, generating extraordinary outbursts of energy that ripple through the universe. This interaction between black holes and matter is among the most spectacular processes in the cosmos, illuminating the sky with light from regions we otherwise could never see. The dance of matter, accretion disks and quasars. At the heart of a black hole's interaction with matter lies the accretion disk, a swirling whirlpool of gas, dust, and other material that forms as matter falls inward, drawn inexorably toward the black hole's immense gravitational well. Unlike the serene orbits of planets around a star, the matter in an accretion disk is caught in a desperate spiral, losing energy through friction as it accelerates to nearly the speed of light. This friction causes the material in the disk to heat up to staggering temperatures, sometimes reaching millions of degrees, transforming the once cool gas and dust into one of the brightest sources of light in the universe. The energy released in these accretion disks is staggering. As matter moves closer to the event horizon, it releases more and more energy, radiating across the electromagnetic spectrum, from radio waves to visible light to powerful X-rays. It is this process that powers some of the most luminous objects in the universe, quasars. Quasars are so bright that they can outshine the galaxies in which they reside, emitting more energy in a single second than hundreds of billions of stars combined. Despite being powered by the gravitational collapse of matter into a black hole, quasars are not simply bright lights in the sky, they are cosmic beacons that illuminate the distant reaches of the universe, allowing us to peer back in time and observe the early stages of galaxy formation. The energy emitted by quasars doesn't just light up the cosmos, it plays a key role in the life cycles of galaxies. The intense radiation from a quasar can heat the surrounding interstellar medium, preventing it from cooling and collapsing to form new stars. In this way, black holes can regulate star formation, acting as a kind of thermostat for the galaxy. By throttling back the supply of cold gas available for star birth, black holes influence the growth and evolution of their host galaxies, ensuring that star formation proceeds at a sustainable pace. Jets of power, black hole feedback and galactic sculpting. As if quasars weren't impressive enough, black holes also unleash some of the most spectacular and powerful phenomena in the universe: relativistic jets. These jets are narrow, focused streams of plasma that are ejected from the regions near a black hole's poles at speeds approaching the speed of light. Though black holes are defined by their inability to let anything escape once it crosses the event horizon, the region just outside the black hole, the accretion disk, can generate jets that extend for millions of light-years into space. How are these jets formed? While the exact mechanisms remain a subject of active research, scientists believe that the intense magnetic fields in the accretion disk play a key role. As material spirals into the black hole, the powerful magnetic fields twist and compress, launching charged particles away from the black hole's poles in tightly collimated streams. These jets blast outward with tremendous energy, cutting through the interstellar medium like a cosmic laser, affecting everything in their path. The power of these jets is difficult to overstate. They can transport vast amounts of energy across enormous distances, shaping the structure of entire galaxies. As the jets plow through the intergalactic medium, they create enormous bubbles of superheated gas, disrupting the surrounding environment and altering the dynamics of star formation. In some cases, the jets can even blow gas completely out of the galaxy, halting the formation of new stars and quenching the galaxy's growth. This process, known as feedback, represents one of the most important ways in which black holes influence the universe. Far from being isolated points of destruction, black holes act as regulators of galactic ecosystems, balancing the forces of creation and destruction. The feedback from black hole jets ensures that galaxies don't grow too quickly or collapse under their own weight, maintaining the delicate equilibrium required for the continued evolution of complex cosmic structures. The cosmic web, black holes and galaxy formation. The influence of black holes extends far beyond the immediate vicinity of their host galaxies. The energy released by accretion disks and jets plays a significant role in shaping the large-scale structure of the universe itself. Galaxies are not isolated islands in space, they are part of a vast cosmic web, an intricate network of filaments composed of dark matter, gas, and galaxies that spans the entire observable universe. Black holes, with their powerful outflows of energy, act as sculptors of this cosmic web, driving the flow of gas between galaxies and influencing the formation of new cosmic structures. In particular, black hole jets can drive material out of galaxies and into the intergalactic medium, where it mixes with the vast reservoirs of gas that fill the spaces between galaxies. This material, once expelled, may eventually cool and fall back onto other galaxies, fueling new bursts of star formation and contributing to the growth of cosmic structures. In this way, black holes play a key role in the ongoing cycle of matter in the universe, ensuring that the building blocks of stars and planets are distributed across vast cosmic distances. The connection between black holes and the cosmic web is a reminder that the universe is deeply interconnected. Black holes, though they may seem like isolated points of infinite gravity, are part of a much larger system of cosmic evolution. Their influence extends far beyond the bounds of their event horizons, shaping the fate of galaxies, stars, and even the vast structures that define the universe itself. Black holes, catalysts of cosmic change. The interaction between black holes and matter reveals a fundamental truth about the universe. Even in the most extreme environments, where gravity warps space and time beyond recognition, there is an ongoing process of creation and transformation. Black holes, once thought to be the end points of stellar evolution, are now understood to be powerful engines of change, driving the dynamics of galaxies and the cosmos as a whole. Through their interactions with matter, black holes generate some of the brightest and most energetic phenomena in the universe. Accretion disks and quasars light up the night sky, revealing the presence of black holes billions of light-years away. Relativistic jets carve through the intergalactic medium, shaping the formation of stars and galaxies on a cosmic scale. And the feedback from black hole outflows ensures that galaxies evolve in a balanced and sustainable way, preventing them from collapsing under the weight of their own gravity. But the story of black holes and matter is not just one of destruction and creation, it is a story of cosmic interconnectedness. Black holes remind us that the universe is a dynamic, ever-changing system, where even the most extreme objects play a vital role in the ongoing cycle of matter and energy. In the end, black holes are not just consumers of matter, they are catalysts of cosmic change, driving the evolution of galaxies and the universe itself. As we continue to study black holes and their interactions with matter, we are reminded of the profound beauty and complexity of the cosmos. The universe, in all its vastness and mystery, is a place where extremes of gravity, energy, and matter collide, creating the structures and phenomena that make the cosmos what it is. And in this dance of destruction and creation, black holes are among the most powerful and awe-inspiring participants. The cosmic philosophy of black holes. The contemplation of black holes inevitably stirs within us a profound sense of wonder and introspection. These cosmic behemoths, with their ability to stretch and twist the very fabric of spacetime, force us to confront some of the most fundamental questions about the nature of reality, existence, and our place in the universe. To study black holes is to peer into the heart of nature's most extreme possibilities, where the known laws of physics break down and where the boundaries of our understanding are pushed to their limits. In this sense, black holes are not merely objects of scientific inquiry, they are gateways to philosophical reflection, symbols of the boundless mystery that the universe holds. Black holes challenge us in ways that no other cosmic phenomena can. They force us to reckon with the unknown, with the idea that there are regions of the cosmos where our current understanding of reality falters and collapses. And in doing so, they remind us of the limitations of human knowledge. Yet, far from being discouraging, this confrontation with the unknown compels us to seek deeper truths, to push the boundaries of our intellectual horizon ever further, driven by a thirst for discovery that has defined humanity's relationship with the cosmos for millennia. The horizon of knowledge. What lies beyond? One of the most evocative aspects of black holes is the event horizon, the invisible boundary that encircles the black hole, beyond which no information can escape. This horizon is not just a physical boundary, it is a metaphor for the limits of our comprehension. As we peer into the heart of a black hole, we are confronted with a region of space where the known laws of physics, those that have guided and shaped our understanding of the universe, no longer apply. Beyond the event horizon lies a mystery, a realm where the flow of time is distorted, where space is compressed to unfathomable densities, and where the very concept of existence takes on strange new meanings. This prompts an inevitable question: what lies beyond the horizons of our understanding? Black holes symbolize the ultimate unknown, a reminder that despite all our advances in science and technology, there remain profound mysteries lurking in the cosmos, mysteries that may take centuries, or even millennia, to unravel. The event horizon is a boundary between what we know and what we have yet to discover, between the comfort of understanding and the awe-inspiring uncertainty of the universe's deeper truths. The notion that there are places in the universe where the laws of physics falter raises another philosophical question: are there ultimate limits to human knowledge? Can we, with our finite minds, ever hope to fully comprehend the infinite complexity of the cosmos? Or are there regions of reality that will always remain beyond our grasp, hidden behind the event horizons of existence? These questions echo the thoughts of ancient philosophers and modern scientists alike, who have long pondered the extent of human understanding. The illusion of finality, the journey of discovery. In confronting black holes, we are reminded that the pursuit of knowledge is not a linear journey toward a final, definitive understanding. Instead, it is a process of continual exploration, where each new discovery opens up new questions, revealing deeper layers of complexity. The illusion of finality, the idea that we might one day know everything there is to know, dissolves when we look at black holes. They teach us that each answer brings with it a multitude of new mysteries, that the universe is an ever-expanding frontier of inquiry. The singularity at the heart of a black hole, a point of infinite density where space and time are crushed into an unimaginable state, epitomizes this idea. The singularity defies explanation with our current theories of physics. General relativity predicts its existence, yet quantum mechanics suggests that something must intervene before reality reaches such an extreme. The tension between these two pillars of modern science serves as a reminder that even our most trusted frameworks for understanding the cosmos are incomplete. But rather than being a dead end, this confrontation with the unknown is an invitation to continue exploring, to refine our theories, and to develop new tools of inquiry. Black holes, in all their enigmatic grandeur, remind us that the journey of discovery is far from over. The singularity is not a conclusion, it is a beginning, a place where the next great leap in our understanding of the universe may emerge. The cosmic perspective, humanity's place in the universe. The study of black holes also forces us to reflect on our place in the cosmos. In the face of such immense forces, of objects so massive that they warp the very fabric of space-time, it is easy to feel insignificant. The universe is vast, and black holes, cosmic powerhouses that can devour stars and shape the evolution of galaxies, seem to dwarf the smallness of human existence. Yet, paradoxically, it is through our study of these distant phenomena that we come to appreciate the uniqueness of our own consciousness, our ability to contemplate the universe and seek answers to its deepest mysteries. This is the cosmic perspective, the recognition that while we are small in the grand scheme of the universe, we are also rare and precious. We are beings capable of understanding and marveling at the cosmos. Black holes, with all their mystery and power, are silent witnesses to the fact that we live in a universe where sentient beings can ask profound questions about the nature of existence. In studying black holes, we are not merely observing distant objects, we are engaging with the very fabric of reality, seeking to understand our place within it. Carl Sagan once said, "We are a way for the cosmos to know itself." In this sense, our exploration of black holes is not just a scientific endeavor, but a philosophical one. We study black holes not only to understand how they work but to understand something fundamental about the universe itself, and about ourselves. We are participants in the cosmic story, connected to the universe in ways we are only beginning to understand. The nature of reality, beyond space and time. As we delve deeper into the mysteries of black holes, we are also led to question the very nature of reality itself. Black holes, with their ability to warp space and time, suggest that reality may be far more flexible and dynamic than we once imagined. The event horizon, the singularity, the possibility of wormholes and alternate dimensions, these concepts push the boundaries of what we think of as real. They invite us to consider that reality is not a fixed, unchanging entity, but something that can be stretched, bent, and reshaped under the right conditions. What does this say about the nature of existence? If space and time themselves are malleable, what does that mean for our understanding of the universe and our place within it? Black holes challenge us to think beyond the conventional boundaries of physics and philosophy, to imagine new ways of conceptualizing reality. They remind us that the universe is not static, but in constant flux, a dynamic interplay of forces and phenomena that shape the fabric of existence. In this way, black holes are not just objects of study, they are symbols of the unknown, reminding us that the universe is filled with possibilities that we have yet to explore. They are a call to adventure, urging us to expand the horizons of our understanding and to embrace the mystery that lies at the heart of the cosmos. The invitation to wonder. Ultimately, black holes represent an invitation to wonder. They are symbols of the unknown, reminders of the vastness and complexity of the universe, and a testament to the boundless curiosity that drives humanity's exploration of the cosmos. To study black holes is to confront the limits of our knowledge, but it is also to be inspired by the possibilities that lie beyond those limits. In the face of black holes, we are reminded of the grandeur of the cosmos, a universe that is at once beautiful, terrifying, and filled with mystery. It is a universe that invites us to look beyond the surface, to ask questions that challenge the very foundations of our understanding, and to seek answers that may forever change the way we see the world. As we stand on the threshold of the unknown, black holes beckon us forward, urging us to explore, to discover, and to wonder. They are a reminder that, despite all we have learned, the universe is far more vast, far more mysterious, and far more beautiful than we can possibly imagine. And in that mystery lies the true joy of exploration, the joy of knowing that, no matter how much we learn, there will always be more to discover. The eternal allure of black holes. As we gaze into the unfathomable depths of the cosmos, black holes beckon to us with a gravitational pull that transcends the physical. They are not merely objects to be studied, they are enigmas that ignite the deepest questions within our minds and hearts. In the grand tapestry of existence, black holes occupy a unique place. They remind us of our own insignificance, yet simultaneously call us to rise beyond it. These colossal voids, where space and time themselves are twisted and contorted to their very limits, are symbols of the vast unknown, a frontier not only of science but of human understanding itself. Black holes, in all their mystery, have become windows through which we peer into the extremes of the universe. They reveal the nature of spacetime and gravity under conditions so intense that the rules of physics as we know them begin to unravel. Yet, paradoxically, it is in this breakdown of understanding that new discoveries are born. Black holes challenge our intellect, forcing us to reconcile the seemingly irreconcilable, the elegant geometry of general relativity with the probabilistic chaos of quantum mechanics. They push us to explore realms of reality that lie beyond the familiar, reminding us that the universe is far stranger, and far more magnificent, than we can fully comprehend. The infinite frontier, exploring the boundaries of knowledge. The study of black holes has already revolutionized our understanding of the cosmos. Concepts like spaghettification, where matter is stretched into thin strands by tidal forces, and the singularity, where time and space cease to exist as we know them, have expanded the limits of what we thought was possible. The discovery of Hawking radiation has opened a new avenue into the interplay between quantum mechanics and gravity, suggesting that even black holes, those ultimate absorbers of matter and energy, may not last forever. And the tantalizing possibility that black holes could be portals to other universes forces us to contemplate the very structure of reality itself. Black holes challenge our long-held beliefs about the permanence of information and the nature of existence. The information paradox, where the fate of matter and data falling into a black hole appears to violate the principles of quantum mechanics, has provoked some of the deepest philosophical and scientific debates of our time. Through their study, we are led to consider the ultimate fate of the universe and our place within it. Are black holes mere endpoints in the life cycle of stars, or do they play a more active role in shaping the cosmic evolution of galaxies and the universe at large? Cosmic paradoxes and human curiosity. For all that we have learned, black holes continue to baffle us. Their very nature defies easy explanation. They are a riddle wrapped in the mathematics of Einstein's equations, enshrined in the unknown physics of quantum gravity. Even as our telescopes and instruments reach farther into the universe, as we observe the gravitational waves generated by black hole mergers and study the detailed dynamics of accretion disks, we are reminded of the limits of our knowledge. We stand on the precipice of understanding, peering into the darkness, but much remains hidden from view. And yet, it is precisely this mystery that makes black holes so compelling. In an era of unprecedented technological progress, when we have sent probes to distant planets and mapped the structure of the universe with extraordinary precision, black holes remind us that the cosmos still holds countless secrets. They are humbling reminders that, despite all we have achieved, we have barely scratched the surface of the universe's complexity. But it is not in the answers alone that we find meaning. The pursuit of knowledge, the quest to understand, is itself a deeply human endeavor. Black holes push us toward new theories, toward the unification of quantum mechanics and general relativity, toward a deeper comprehension of the forces that shape the cosmos. They invite us to journey into the unknown, to question our assumptions, and to embrace the uncertainty that lies at the heart of discovery. They remind us that the beauty of the universe is not found solely in what we know, but in the mysteries that compel us to keep searching. A cosmic dance of discovery. As we continue to study black holes, we are not merely unraveling the secrets of gravity and spacetime, we are deepening our connection to the cosmos itself. Black holes are more than just phenomena for physicists to study, they are cosmic symbols, embodying the boundless curiosity that defines the human spirit. They speak to our inherent desire to explore, to understand, and to transcend the limitations of our knowledge. In a universe where every answer seems to generate new and more profound questions, black holes stand as a testament to the eternal nature of discovery. There is something deeply poetic about our relationship with black holes. Though they are the ultimate consumers of matter and light, devouring everything that crosses their event horizons, they give back to us in the form of knowledge and wonder. Their existence compels us to think in new ways, to challenge the very nature of reality, and to confront the vastness of the unknown with both humility and awe. In studying black holes, we participate in something far larger than ourselves. We engage in the unfolding story of the universe, a story that has been written across billions of years and stretches beyond the horizons of our imagination. The allure of black holes is not just scientific, it is existential. They remind us that we are part of something far greater than our individual lives, part of a cosmic dance that transcends time and space. The eternal allure, a future of infinite possibility. As we look to the future, the allure of black holes remains eternal. They will continue to draw us in, not just with their gravity, but with the promise of discovery. Their study is a never-ending journey, one that will lead us to new theories, new insights, and perhaps new ways of understanding the universe. The event horizon is not just a boundary in space, it is a symbol of the frontiers of human knowledge, always just beyond our reach, yet forever pulling us closer. And so, as we move forward in our exploration of the cosmos, black holes will remain among the most fascinating and mysterious objects in the universe. They will continue to challenge our intellect, inspire our curiosity, and expand the horizons of what we thought possible. In the face of their profound mysteries, we are reminded that the universe is a place of infinite wonder, where every answer leads to deeper questions, and every discovery brings us one step closer to understanding the vast, interconnected web of existence. In this journey, we are not mere observers of the cosmos. We are participants in its grand unfolding, drawn ever closer to the event horizon of discovery by our insatiable curiosity and our desire to know the universe's deepest truths. And in this, we find not just knowledge, but meaning, a connection to the cosmos that speaks to the very essence of what it means to be human.